Hey everyone. So in this video, I'd like to talk about linear functions. So far we've been talking about general qualities of functions, broad ideas like domain and range, transformations of functions, inverses, and I want to turn to start talking about specific examples of functions and apply these ideas to specific examples of functions. And I'd really like to begin with probably the most basic example of a function, but still very important, linear functions. And so here I've got this statement that says that suppose that some mailing service has some fee for shipping packages, and there's a $5 cost for just the service of shipping a medium-sized package, and there's an additional 40-cent fee for every additional pound of that package. And so there's a relationship here between the cost of mailing this package and the weight of the package. Right here we might notice that it feels like the cost depends, right, the cost of shipping the package depends on the weight of the package. And really this means that the cost is a function of the package's weight. All right, so here let's explore describing this function in different ways. But first things first, to really get a grasp of describing this function, we really ought to define some variables here. So here, let's say that the weight of the package is given by this variable w. So here, let's let w represent the weight of the package in pounds. And here, let's use c to represent the cost of shipping that package in dollars. And I think we probably get the best sense of how this function works just by getting a look at a few different points on this function. So here, maybe we can describe this function as c of w, right, is the cost of this shipping this package with a weight of w. Right, so here, that's going to be our output for our function. And here, w can be our input. And so how much does it cost to ship a package that weighs 0 pounds? So it feels a little silly, but this idea of the fee for sending this package is that it's going to cost $5 just for the service, right? Regardless of the weight, it's going to cost $5. And so, as silly as it sounds to send a package that weighs 0 pounds, it's going to cost $5. And I can imagine this as being 5 plus 0.4 times 0, right? There's $0.4 per pound, 0.4 or 40 cents per pound that should be added on to the cost. But there's no weight here, so that part's not super relevant. But here, if I have a weight of 1 pound for this package, we see that, well, to compute the cost of the package, I'm going to add on one set of 40 cents to our initial $5 fee, right? So this is 5.40. And for a 2 pound package, we have 5 plus 0.40 times 2, right? 2 sets of 40 cents added on to $5. This gives us 5.80. 3 gives us 5 plus 0.40 times 3 for $6.20. And we can keep this going, but maybe you get a sense of how the rest of this table looks. And we can maybe look at a general example. If I plug in some value w, well, how do we compute the cost corresponding to that weight of w? Well, it would be $5 guaranteed for just shipping this package, and then 40 cents for every pound of this package, or the weight of this package. And so really this is kind of like our function here. This is an equation for our function. We can write this as C of W really is equal to, right, the cost is really going to be $5 plus 0.40, so 40 cents per pound. And so here, one thing we can notice is that there was this $5 here. This was the initial cost. Right, this was regardless, it didn't care about how much the package weighed. You're paying this no matter what, regardless of the input. And then here, this 0.40, this was the cost, the additional cost per pound of this package. We can kind of think of this as the rate of change. Right, it was the cost or the price, additional price per pound. This was a rate of change here. And notice, one thing I really want to point out is that the rate of change in the past we talked about average rates of change. We looked at functions that were sort of varying quite a bit. And when we computed the average rate of change of these functions, sometimes they ended up different depending on the intervals we used, the intervals of our input that we looked at. And so here, the rate of change of this function is constant. This rate of change is not changing, right? So if I compute the rate of change, if I look at let's say I take this point here, and maybe let's do this point out here, and I compute the average rate of change between these 2 points. It's going to be the same regardless of actually what 2 points I choose. Right, so here, if I compute the average rate of change, right, recall that the average rate of change well, this is equal to the change in the output of the function divided by the change in the input of the function. And so we've seen this as y2 take away y1 over x2 take away x1 if we have 2 points, x1 y1 and x2 y2. And this is also the same as if we're talking about function notation. We can think of these y values as outputs. So the output corresponding to x2 take away the output corresponding to x1 divided by x2 minus x1. So this is another way of talking about the average rate of change. But if we take our 2 points above, one of them was this point 1, 540, and another one was the point 3, 620. Well, then we can compute the average rate of change between these 2 points. And it doesn't matter which order we use, right? So I can kind of call this maybe my first point and this maybe my second point. We would get the change in the output is the difference between the output values, 620 take away 540. And then I just have to be consistent with my ordering here, that here, I'm calling this my second y value. I'm going to use my second x value here. So 3 take away my first x value, 3 take away 1. Well, we get 0.80 divided by 2. In other words, 0.40. Right, so we see that same rate of change, 40 cents per pound. Right, that's the same regardless of what 2 points I'm going to use. I'm going to get that 40 cents or 0.40 dollars, right, the output per pound, the input. Okay, so we've made a list of ordered pairs of our function. where we looked at the different weights of the packages we might ship and their corresponding costs to ship them. We also looked at, using this table, we built an equation for this function. I don't want to dig so much into graphing right now, but here's a graph of this function. And really one thing I want to point out is that the graph of this function is a line, right? It's a straight line. And so here, for this reason, we call this function c of w. It's an example of a linear function. Right, so functions whose graphs are straight lines, so has a line as a graph. And then the other thing I wanted to point out was, we talked about this idea that function had a constant rate of change. No matter what 2 points I used on or ordered pairs for my function, we got the same rate of change no matter what. And so any function that has a constant rate of change, that's really an example of a linear function. And so really, in general, any function that can be put in this form f of x is equal to m times x plus b is an example of a linear function. Right, so there's some coefficient to our input variable. And we saw in the previous example, we saw that this really represented the rate of change, that constant rate of change that's the same throughout our entire graph. That's the case for a linear function, and it's this coefficient to our x, our input variable. And so sometimes this also gets called the slope. And then we also notice that here there's this constant term added on, and this corresponded to some sort of initial value. Really, it's the output when the input is 0. So let's take a look at another example here. We have this word problem that says, to prepare for a trip, Sandra filled up her 19-gallon tank. She estimates that her vehicle will use about 3 gallons per hour, and we want to find an equation for the amount of fuel in Sandra's tank after t hours. So there's a lot of information here, but we want to build an equation relating the amount of fuel in the tank to the amount of time that has passed that Sandra spent driving. And so here, this is an example of a function, and we want to make sense of what can represent an input and what can represent an output. And the idea is that when we're talking about a function, the outputs really should be able to be determined by the input. They depend on the input. And really it feels like the amount of fuel in the tank depends on or can be determined by the amount of hours that have passed. So really we want to think about this fuel quantity as an output and the amount of time that has passed as an input. Really the amount of fuel in the tank this depends on is a function of the amount of time that has passed. So here maybe I'll use the g variable to represent the amount of gallons of gasoline that Sandra has in her tank. And so this equation should look something like g of t is equal to, and here it's a linear function. How can we tell that it's a linear function that we can use to represent what's going on here? Well, she estimates that her vehicle will use about 3 gallons of gasoline per hour. Right, so here, this 3 gallons of gasoline per hour, this is a rate of change, right? It's gallons per hour, the amount of output values changing per the amount of input values changing. Gallons per hour, it's a rate of change. And we've got a linear function because this is a constant rate of change, right? It's not, the rate of change is not changing up and down, it's this constant value 3. And actually, I want to be a little bit more careful here because it says that she's going to use this much gallons of gasoline per hour. And so here, if we're trying to figure out this rate of change, this value for this rate of change, it's not just 3 gallons, it's actually negative 3 gallons. Right? This fact that she's using 3 gallons, we expect the amount of gasoline in her tank to decrease as she's driving. So here, if I'm going to write a function here, m times t plus b, where m is this rate of change, then this rate of change here is negative 3. She's using 3 gallons of gasoline per hour. Now the next piece of information that we can use to build this equation is that she's filled up her 19-gallon tank. Right, so starting this trip, she has 19 gallons of gasoline in the tank. Before any time has passed, before she's used up any amount of gasoline, she has 19 to begin with. So this is like an initial amount. It's like the output, the amount of gallons in her tank, when the input is 0, when t is equal to 0. That's this value b. It's 19. And so here we already have the equation now. We have g of t is equal to negative 3t plus 19. And here, maybe just to convince ourselves that this is an equation for this function, for this situation, let's make this ordered pair, this list of ordered pairs, a table here where I have t and g of t. And maybe let's forget about the equation we've just found. Let's just make this table of values of what we really anticipate or expect for the relationship between the time that's passed and the gallons of gasoline in the tank. Right, we know that when 0 amount of hours have passed, there should be 19 gallons of gasoline in the tank. When 1 hour has passed, we expect her to use 3 gallons, there should be 16 gallons of gasoline in this tank. 2 hours have passed, there should be 13. 3 hours have passed, there should be 10. And really, if you think about this, what's going on here is we've got 19 take away 3 times 0. 19 take away 3 times 1. 19 take away 3 times 2, and so on. And for some value of t, for any value of t, really it's the amount of gasoline in the tank is 19 take away 3 times t. That's how we're going to compute the output. And this feels a little bit reverse of what we're looking at when it comes to our function here. But notice that, we can rearrange this order, right? This is really the same thing as negative 3t plus 19, which is what we have for the expression of our function. And so here's the graph of our function if the horizontal axis corresponds to t, the number of hours that have passed, and the vertical axis tells us the number of gallons in the tank, so g of t. And we can see that this line is going down from left to right. It's an example of a decreasing function. And notice that when we talk about a linear function, the rate of change is always going to stay the same for this function. And so really, we can see that that for a linear function, it's increasing if the rate of change is positive, if the slope is positive. And we saw this example for one of our previous graphs, right? Here we have this graph of the cost to ship a package with weight W, and we saw that the rate of change was 0.40. The cost increased by 40 cents per pound, and we can see that the rate of change here is positive. The graph of this function, it's increasing. Whereas here for this function, we saw that the rate of change was negative. We had a rate of change of negative 3. They were losing or using 3 gallons of gasoline per hour. So here we can say that a linear function is decreasing if the rate of change is negative. Okay, so let's continue with this idea of rate of change. So I know that some linear function, when I input 3 into this function, I get an output of 2. And when I input 0 into this function, I get an output of 4. And so here, when we want to find the rate of change, and here I'm not saying average rate of change because for a linear function, the rate of change is always the same. And so we can just call it the rate of change, not the average. And so the rate of change, right, it's the change in the output divided by the change in the input, and we listed that as y2 take away y1 over x2 take away x1. We can also write this as f of x2 take away f of x1 divided by x2 take away x1, right? This is the slope of this linear function. And here I can kind of think of this ordered pair, or this piece of information as an ordered pair. Maybe my first one, and this piece of information as another ordered pair, maybe a second ordered pair. And I can use this to compute an average rate of change for, or not an average rate of change, the rate of change for this function. Right, so I take my output 4 and I subtract away my other output 2. And I'm consistent about my order here. I take my input, my second input, and subtract away my first input value. And what we get out is this, we get 2 over negative 3, and here I'm going to write this as negative 2 over 3. It just feels preferable to me. Right? Maybe just to remind you that if you have negative of some fraction, this is the same as negative of the numerator or over the denominator, or the numerator over the negative denominator. These are all the same thing. So this is the rate of change of this linear function. Can we do better than this? Can we find the equation of this function? Well, here, if I know this is some linear function, it's going to be of the form f of x is equal to m times x plus b, and we figured out the rate of change. We figured out that this is negative 2 over 3. What we're missing here is this initial value. Right, so it's some initial value. And what I mean by initial is it's the output when the input is 0. And so if we look back at our 2 pieces of information that we started with, we actually were given this. We were given that the output when the input was 0 is 4. Right, so here, this linear function is actually f of x is equal to negative 2/3 x plus 4. And we can check this. Right, so this is supposed to be a function that satisfies the conditions above, that what was it? It was f of 3 is equal to 2 and f of 0 is equal to 4. Well, we can plug in those values, right? We can check if I input 3 into my function, do I get out an output of 2? And I can also check that if I input 0 into my function, do we get an output of 4? Right? Does it satisfy both conditions for this function? And we can see for this second example, if I plug in 0, well, 0 times negative 2 over 3, that's going to be 0. Oh, sorry, this should have been 4, right? If I plug in 0 into my function, I'm expecting 4 out. Right? I want to check that this condition is true. And we can see that the second condition is true, that when I plug in 0 for my input, multiply by negative 2/3, I'm still going to get 0, and then plus 4, I do get 4, right? So this point satisfies my function that I've determined. What about this first example? Well, if I plug in 3, I get negative 2 divided by 3, then multiplied by 3. Those undo each other, and I'm just left with negative 2 plus 4 on the right, and 2 on the left. Well, negative 2 plus 4 is 2, and so we get 2 out. This function, it takes both of the inputs we started with and takes them to the outputs we expected. So this is the equation for the linear function we were looking for. So let's do the same thing, but for this function that we see graphed below, this function h of x. So we want to determine h of x is equal to, we want to figure out the values of m and b for this linear function, right? We see that it's a line here. We just need to figure out the rate of change and some sort of initial value. And so I can see b right away. Right, this is supposed to be the output when the input is 0. And we can see that point here. We see that this is -3. And then this m value, this rate of change here, well, what do? We take 2 points that we see clearly on the graph of this function. Right? These are 2 points where I can see the inputs and the outputs. And so we can find the rate of change between these 2 points, and that'll be the rate of change of this linear function. And so the rate of change here, again, it's the change in the outputs divided by the change in the inputs. So here maybe I'll label this, maybe I'll label this my second coordinate and this one my first point. And so the second point here, right, this is the point 2, 2. And this first point, it's the point 0, -3. And so if I find the rate of change between these 2 points, I get 2 take away -3 divided by 2 take away 0. And this gives me 5 over 2, right? 2 take away -3, that's the same as 2 plus 3. And then I have 2 take away 0. And so this is the rate of change here, 5 over 2. And we can see this here as the fact that this graph is going, or between these 2 points, the graph is going up 5 units. Right? Its change in its output is 5 units for every change of 2 in the input. And so our linear function, our equation for this linear function is h of x is equal to 5 over 2x minus 3, right? The b value is the output when the input is 0, sometimes called the vertical intercept. It's a value of -3. So here we've seen 2 examples where we're given that vertical intercept, that initial value. But what happens if we're not given that? How can we still find an equation for such a function? And so here let's take a look at an example of how that really works. So here again we have 2 points. We see that an input of -1 leads to an output of 4, and an input of 5 leads to an output of 2. We can again find the rate of change. So here if I take my output of 2 and subtract away 4, and I take that and divide it by my input of 5, subtracting away -1, I get -2 over +6. In other words, -1/3. Right, so this is the rate of change of my function f. And here maybe I didn't say this, but I'm looking for an equation of a linear function. And so here finding this rate of change really determines a key piece of the equation for this linear function, because the rate of change is one of the coefficients in the equation. And so here we figured out the rate of change is -1/3, so we know that f of x looks like -1/3 x plus some initial value that we don't see here immediately. It's not 4, it's not 2. Really, this is supposed to be, this value of b is supposed to be the output corresponding to an input of 0, and we just don't see that point quite yet. But earlier we had a function and we checked that 2 points satisfied the function. Really, the idea is that this equation, it's supposed to be one that takes this value, this input of 5, and brings us to an output of 2. And this equation is supposed to take an input of -1 and bring us to an output of 4. And so we can use this fact to figure out what b needs to be to bring our x value of 5 to a y value of 2, or an x value of -1 to a y value of 4. This function must make the points satisfy this function. The equation of this function, the points must satisfy this equation. if this is really going to be an equation of the function. And so here, let's go ahead and do that. Maybe I'll take -1. I'll use this point here. I'll take -1 for my x value, and I know that if this is really going to be an equation for my function, then it really should take that input value of -1 to an output value of 4. It has to. This must be the case if this is going to be the equation of our function. And so we can work this out to solve for b now, that b is really the only variable missing piece of information for this equation here. And so here I have 4 is equal to, well, -1/3 times, -1/3 is, -1/3 times -1 is +1/3. And so subtracting away 1/3 from both sides, you get 4 minus 1/3 is equal to b. And so 4, that's the same as 12 over 3, right? 12 divided by 3 gives us 4, so I can rewrite 4 as 12 over 3. And this is beneficial for us because 12 over 3 take away 1 over 3. Those have the same denominator, and I can actually perform the subtraction by subtracting their numerators. And I get 11 over 3 is the value of b. So this tells us that the equation for this linear function, well, we determined the slope was -1/3. We determined the initial value, the b value is 11/3, and so here we have the equation of the linear function. So let's take a look at this other example here. This word problem says that Sonia is walking home from a friend's house, and after 2 minutes, she's 1.4 miles from home. And then 12 minutes after leaving her friend's house, she's 0.9 miles away from home. So we want to find an equation for Sonia's distance from her home after t minutes. And so here, maybe we can use t as the variable for time. She's spent walking in minutes. Maybe we can use a d variable here for her distance from home. In miles. And so we want to find an equation relating d and t together. And here we're going to talk about this idea in terms of functions. We want to describe how one variable depends on or is determined by another. And really, this idea is that the distance she's traveled really depends on the amount of time she's spent traveling, the amount of time she's spent walking. And so here I would say d, her distance, is going to be the output of this function, and t can represent the input. Right, so we're really looking for d of t is equal to, and here we're looking for a linear function. Right, so she's likely walking the same pace throughout her entire trip home. So here I can think of this as d of t is equal to m times t plus b. So we want to find a rate of change, and we want to find her initial value. Really, maybe just to talk about this initial value a little bit more, right? What is this initial value going to mean? It's going to mean her distance she is away from home when she hasn't started walking yet. Right? Really, this b value represents how far away from home before she started walking, or while she's at her friend's house, essentially. And here, this is sort of her rate of change of distance over time. It's how fast she's walking. Really her pace, her speed. And so here, how do we compute this rate of change? Well, we take these two pieces of information. Right? There's sort of one point here. She's 1.4 miles from home after 2 minutes. So this is kind of like the point 2, 1.4. And then she's 12 minutes after leaving, she's 0.9 miles from home. So this is like the point 12, 0.9. And so we can find the slope between these 2 points. I'm going to go ahead and take 0.9 minus 1.4, and I'm going to divide that by the change in the input value, so 12 take away 2. And we get, well, 0.9 take away 1.4, that's negative 0.05. No, oops, sorry, this is negative 0.5. And then we're going to divide that by 12 take away 2, that's 10. And negative 0.5 divided by 10, well, that's negative 0.05. So this is her rate of change. This is how fast she's walking. This is negative 0.05 miles per, we're talking about her change in her input values is described by minutes. And so this negative value here, it kind of makes sense, right? Why does that make sense? It's talking about the distance she is away from home. Well, if she's walking home, that distance should decrease. Right? This should be a decreasing function because she's walking towards her house. Okay, so here we have her rate of change. We have d of t is equal to negative 0.05 times t plus b. And now we just need to figure out this initial value. Well, if this is going to be an equation for our function, right, we know it should make these points true. These points should satisfy the equation. In other words, it should take an input value of 2 and bring us to an output value of 1.4. Or it should take an input value of 12 and bring us to an output value of 0.9. And so here, let's go ahead and take this point 2, 1.4. If I input 2 into this function, I should get 1.4 out for this function. And so now, with that in mind, knowing that that must be true, we can find the value of b. And so 2 times negative 0.05 is negative 0.1. And so when I add 0.1 to both sides to get b alone and figure out that, that initial value, well, what I get is b is equal to 1.5. So her friend's home was 1.5 miles away from her home. And this tells us that the function we're really looking for is d of t is equal to negative 0.05 t plus 1.5.